Bismillah, Assalamualaikum warahmatullah. You're listening to the Philosophy of Science lesson on logic and mathematics. The outcomes for this topic are two. First is for you to describe the basic principles of deduction, induction, and abduction. So you have an exposure to logic and mathematics. And secondly, for you to be able to relate both logics and mathematics to philosophy of science. Our very first question would be, what do we mean by logic? You can think of logic as the study of relationship between thoughts. So logic can get very technical, very complicated. But for us to go through our daily experience, we just need to learn a few basics and then build up from there. I want you to think of logic like mathematics. So most of us don't need to understand complex mathematical calculus to live, to have a meaningful life. But it is helpful to have a strong foundation in, say, arithmetic and some understanding of statistical probability. So if we have those mathematical understanding, we can go through our financial transactions, for example, and make reasonably good decisions with our money. So the same goes for logic. As a matter of fact, we use logic every day in our life already. We use logic every time we are trying to make mental connections between events, either empirical events out there or events that we experience in our mind. And the aggregate of those mental connections, we form beliefs from them. So our religious beliefs, our scientific beliefs rely on our logical skills. And then we make decisions every day based on those beliefs. And most significantly, we take actions based on the decisions that we make. And that affects our lives. So that's why I think it's worth it to learn a bit about logic. The first logical concept that will be useful is called inference. So in its simplest form, you can think of inference as a movement from one thought to another. For instance, you see a married couple. You accept a premise that says Laila is Mark's wife. And from there, you make a conclusion that Laila knows of Mark. So that movement from thinking Laila is Mark's wife to the thought that goes Laila knows of Mark, that movement is an inference. We can also use the verb form of the term inference as well. The verb form of inference is to infer. So here you can say that because Laila is Mark's wife, I can infer that Laila knows of Mark. Now, when you make a logical inference, you want to pay attention to what is called presuppositions or hidden premises. So these are unexpressed statements. So these are statements that are present in your argument even when you don't say them out loud. So as a logical thinker, you want to train your mind to detect these hidden premises. If we go back to the example that we just used, we accept the premise that Laila is Mark's wife. From there, we infer to the conclusion that Laila knows of Mark. But within that inference, there is at least one hidden premise. So that hidden premise goes, wives know of their husbands. So here we presuppose that when you are married to your husband, you know of your husband. At the very least, you know that your husband exists. If you reject that second premise for whatever reason, right, then you cannot move your thought from premise 1 to the conclusion. So that's the importance of hidden premises. Even if hidden premises are not stated explicitly, they are involved in your inference. I've been mentioning the word premise a couple of times now. So what's that? A premise is a statement that has truth value. If you think about it, statements can come in different forms. So there are statements which cannot be true or false. So those statements are not premises. So for example, if someone says to you, please take a seat, that is not a premise. The same goes for a multitude of other expressions like, oh my God, or questions like, how is it going? So all of those are not premises. On the other hand, premises are statements that have truth value, which means we can consider whether it is true or it is false. A clear example would be when we say, Stephen Strange is a surgeon. It can be true that he is or that he's not. Once you understand what premises are, you can use them to make a logical deduction. A deduction is when all the premises are true, the conclusion must be true. For example, premise 1, all surgeons are doctors. Premise 2, Stephen is a surgeon. So, if both premises are true, then it is necessary that Stephen is a doctor. So deduction is one of the most powerful forms of logical inference. When it works, it gives us absolute truth, at least in the logical sense. So we use deduction in kalam, in theology, and other formal sciences like mathematics and computer sciences. There are at least three forms of deduction. We have syllogism, modus ponens, and modus tollens. The first form, syllogism, it has three components. It has a major premise, a minor premise, followed by a conclusion. So in our example, premise 1, all surgeons are doctors, is the major premise. It is a general, a universal statement. Premise 2 is a more particular or specific statement because we are saying that a specific Stephen is a surgeon. We're not talking about everyone. We're not even talking about all Stephens in the multiverse, right? We're only talking about a particular Stephen. And if we accept both the major premise and the minor premise, we can syllogistically conclude that Stephen is indeed a doctor. The second form and the third form of deduction later, they relate to conditional statements. Conditional statements are if-then statements. For example, for modus ponens, premise 1 goes, if the virus infects the body, then the immune system responds. Premise 2 says, the virus infects the body. If premise 2 is true, we can deductively conclude that, therefore, the immune system responds. So these P and Q, they are logical variables. They represent a statement, a premise. So think of them like in math, right? In algebra. In algebra, you've got something like x equals, y plus 1, right? So the x and the y, they are numerical variable, meaning you can put any number to replace x or y to see whether the equation is true. So similarly here, you can put any statement for P and Q to test its logical equation. Now compare that modus ponens with modus tollens, which has negating conditional statements. For example, premise 1, if the virus infects the body, then the immune system responds. Now, premise 2 denies the consequent, denies the Q. Basically, we're saying there is no immune response. So if we accept premise 1 and premise 2, we conclude that, therefore, the virus did not infect the body. Now, other important properties of deduction are its validity and soundness. So listen to this carefully. Premise 1, all surgeons are doctors. Premise 2, Stephen is a surgeon. Conclusion, therefore, Stephen is an avenger. Now, you should sense something's wrong here. But if you look at the premises, they are both true. And the crazy thing is, we can even say that the conclusion on its own is also true. Stephen Strange is an avenger. But something is off here. So what went wrong? What happens here is not the problem with the content of the argument. The problem here is with the structure. Here, you cannot infer the conclusion based on premise 1 and premise 2. You cannot deductively conclude that Doctor Strange is a member of the Avengers based only on accepting that all surgeons are doctors and Stephen is a surgeon. So in cases like this, we say that the deductive structure is invalid. The validity of an argument is about the structure of the argument, not the content. For an argument to be valid, the truths of the premises must structurally guarantee the truth of the conclusion. If the structure of the argument fails to do that, then it is not a successful deduction. And as we have seen in the example, when we analyze the validity of an argument, we ignore the content of the premises and the content of the conclusion. We reject the argument on the ground that the argument is invalid. Now think about the structure of this argument. Premise 1, all surgeons are cocaine addicts. Premise 2, Stephen is a surgeon. Conclusion, therefore, Stephen is a cocaine addict. What do you think of its validity? This deduction is valid, right? Why? Because it satisfies the syllogistic form. You've got your major premise for premise 1, your minor premise for premise 2, and structurally, if both premises are true, you must infer that the conclusion is true. So in terms of validity, we have no problem here. The deductive structure is valid. But if we pay attention to the content, then it is reasonable for us to reject this argument. Why? Because the content of the first premise is false. Not all surgeons are cocaine addicts, right? At least not in Earth 616. So because premise 1 is false, even when premise 2 is true, we must reject the conclusion. And even though this is a valid deduction, we reject it on the ground that the argument is not sound. So unlike validity, soundness is about both the structure and the content of the argument. For an argument to be sound, you must make sure that number 1, the structure is valid, and number 2, the contents of the premises are true. I encourage you, after you finish listening to this episode, I encourage you to go online and look up other examples of validity versus soundness. What you will notice is that all sound arguments are valid, but not all valid arguments are sound. Over time, the more you study science and philosophy of science, you're going to come across paradoxes. A paradox is when you try to follow logic, but the conclusion is weird. So a paradox is when a logical reasoning leads to counterintuitive conclusion. A prime example of logical paradox is what's called the liar paradox. So it's when someone says to you, I am lying right now. If you say that to me, are you giving a true statement? If you are lying, it means you are giving a false statement. But if you are giving a false statement, it means you are lying. But that's exactly what you're saying here, right? You're saying you are lying, which means it is a true statement. But if this is a true statement, then it is true that you are lying. But if you are lying, it means it's a false statement. You see? So it goes into a confusing circle. So there are loads of examples of paradoxes like that, and many of them cannot be solved. In empirical sciences, at times you also come across paradoxes. I call them scientific paradoxes because I want to differentiate it from the logical paradoxes before. For example, in immunology, one theory is that our immune system has memory. Because it has memory, when you get a similar infection the second time, your immune response is stronger compared to the first time. So that makes logical sense, right? Our soldiers have fought the enemy the first time. Now the second time, the soldiers fight better because they have the memory. But again and again, we find cases where our immune response is weaker. So we've seen this in influenza cases, we've seen this in COVID-19 cases. Why? For the same reason. Because the immune system has memory. The memory of the original antigen weakens the clearance of the second infection. So think of it like this. Our soldiers remember the enemy's faces the first time. Now, the second time, similar enemy comes again. The enemy's faces are now slightly different, right? But similar enough with the enemy's faces from the first time. That similarity paradoxically confuses our soldiers. And because their memory confused them, the soldiers fight worse the second time compared to the first time. Now, the wisdom of thinking about paradoxes is this. The fact that paradoxes exist, it indicates that our reasoning faculty is not perfect, and that reality is ultimately beyond what we can understand through rationality alone. So that's such a key principle that you want to have when you read about science or when you have any logical, rational discourse. Even though deduction is amazing, we can't use it all the time. In fact, most of the time in empirical sciences, we use induction. And induction is that when all the premises are true, the conclusion is probably true. Now listen carefully. The conclusion is not necessarily true, only probably true. In empirical sciences, we use the type of it that's called inductive generalization. It is when we move from specific observations to a general conclusion. So usually we take several samples into our lab and we run experiments on them. And from the results of the experiments, we make a general scientific theory, even though we only study a small or a limited number of the samples. And we also use past observations to predict future observations, meaning that when we share our experimental procedures in an academic paper, for example, we assume that if other scientists repeat the same experimental procedures, they will get the same results in the future. An example of induction is this. Premise 1, this vaccine protects most clinical study participants against virus X. Premise 2, I took this vaccine. And from there, you infer the conclusion that therefore I'm likely protected against virus X. So here, it is still possible that even if I took the vaccine, I still get sick from the viral infection. Because in induction, even when all the premises are true, there is still a chance that the conclusion may not be true. One crucial question that you want to ask is, what is the limit of induction? Is it logically necessary that experiments that we do in the lab will resemble true phenomena outside of the lab? Or is it necessary that our future observations will always resemble the past observations? So the answer to questions like those is generally no, and that leads to what is referred to as the problem of induction. I'll leave references for you to explore, so that is sort of a homework, but the basic idea of the problem of induction is this. We can't ultimately justify the truth of our inductive conclusion, and that applies to scientific theories that we get from empirical sciences. We cannot justify scientific theories as a logical necessity about reality. Since we rely on induction in empirical sciences, we unfortunately have to assume certain foundational beliefs that are problematic. For example, when I pipette a drug into a cell culture, I assume the changes inside the cells are necessarily caused by the drug, right? But many scholars have pointed out the flaw of that logic. So for example, you have Al-Ghazali in the 12th century who pointed out that just because two things happen one after the other, it doesn't mean that one necessarily causes the other. And that argument is later popularized in Europe around 500 years later by another scholar called David Hume. The main point here is empirical sciences cannot provide absolute logical truth, but it doesn't mean we should abandon induction altogether. We just need to readjust our expectations about scientific theories. So we don't say scientific theories provide the absolute truth. We simply say that scientific theories are true enough that they match our sense experience so far. And secondly, our scientific theories are true enough that they help us make future predictions, which allow us to build technologies so that we can, stream movies on our phones and get AI to do our homework. Besides deduction and induction, there is another type of logical inference that we use in science. When you get data from scientific studies, scientists can infer more than one explanation from the very same observations. So when this happens, scientists would choose or infer the best explanation. So this inference to the best explanation is what we call abduction. A simple example of abduction is when doctors do a differential diagnosis. So if a patient presents with a runny nose, low fever, and no other symptoms, the doctor can conclude that he has a common cold. So logically, you can inductively argue that the patient has something else, some rare diseases or genetic disorders that may show up as similar symptoms, and you're not wrong. But by applying abduction, the doctor will not come to those rare conclusions, at least not until she observes any additional symptoms. So that's the value of abduction. All right, I'll continue in the next video. Barakallahu li wa lakum. Wassalamu alaikum wa rahmatullah.